So this is a course on quantum information and quantum error correction. So there will be some topics on quantum information as we've been looking at so far, but then also some more specifically tied to quantum error correction. And this is the first one on error correction. It's an introduction to a very simple kind of error correcting code, which actually isn't all that much use in the quantum case, but it can be used as an initial step from which we can then generalize to more useful quantum things. Also, it can be used in this current age of quantum computing, where devices actually exist and you can go and play with them. It can be used as a way of benchmarking them, as a way of getting a perspective on the noise, seeing what noise is there and how well it can be corrected. And a nice thing about introducing this topic so early in the course is that it allows you to go and do some experiments like that yourself, either by creating them in your own way or by using some software that I already have created for implementing large-scale repetition codes, and that you will find on my GitHub. So that's the Dikadoku GitHub. But anyway, let's proceed. What is error correction? So error correction is correcting errors. Suppose you're talking on the phone and it's a noisy line. You need to send a bit of information, so a yes or a no typically. Then how would you make sure that that information gets through? Well, you could repeat yourself. You could just say yes many times or no many times. And then, despite the noise, you can be quite sure that it still sounds like a torrent of yeses or a torrent of no's, and therefore will still be understood as what you wanted it to be. So let's assume a very simple noise model in which there's some probability p that your no is changed to sound like a yes and your yes is changed to sound like a no. Quite unrealistic, but quite a simple noise model anyway. Yeah, that's the noise model we're going to assume. And then to work out whether this p is too much, we have to also think of another probability. How much do we care about being misunderstood? And we're going to call that big P sub a. So if you're not really paying attention to what's going on in the phone call anyway, then you probably don't care. If your yeses sound like no's, you probably don't even know what you're saying anyway. You're just watching TV at the same time, not really paying attention to the conversation. In that case, your maximum acceptable error probability would be very high, and so probably little p is below it and you don't bother with any error correction. But if this noisy line is some radio equipment that you've set up in the jungle where you're conducting a war and you need to pass on some orders in a life or death situation, then your little p, the probability of the noise, is probably much higher than your big P sub a, the maximum acceptable error probability. So you will have to do something. Either you set up a new telecommunications network which has less noise, which probably isn't doable in that scenario, or you find some way to use the noisy line to send information with less noise. So yeah, what do we do? And one way is the repetition code. So using an error correcting code is basically what we need to do. And one great error correcting code, or at least very simple and easy to use one, is the repetition code. It's just to repeat yourself, as I said earlier. Say lots of no's and it'll sound like you mean no, even if some of them are destroyed by static, even if some of them are warped to sound like yeses. If there's lots of no's, it'll still sound like a no, and lots of yeses will still sound like a yes. How do you write no's and yeses? Any way of doing it always looks a bit wrong. Anyway, that's a completely different issue. So when you do that, your message becomes tolerant to small faults. So if you used one yes or one no, just one word to convey your information, then if that gets disrupted by noise, that's it, your message is gone. If you use a repetition, if you use many words, and some of them can get destroyed, but your message still, your meaning still passes through. So in the repetition code, typically the receiver will interpret the message using majority voting. So if they hear a lot of yeses, in fact more yeses than noes, they'll think you're saying yes, and if they hear more noes than yeses, they'll think you're saying no. So the only way you can be misunderstood is if noise causes the majority to flip. So remember, we're just considering a very simple form of noise in which with some probability p, yeses become noes and noes become yeses. So if we have d repetitions, then the probability of the majority flipping, well, we have to look at all possible numbers that can flip that are in the majority. So we consider n is the number of flips, and we go from d over 2. D is the number of repetitions, so we go from d over 2 to d. So we consider all of the cases where the number of flips are in the majority, either half of them flip or more than half of them flip. And then in each of these cases we have the p to the n is the probability that the flippers flip, and 1 minus p to the d minus n is the probability that the ones that aren't flipping don't flip. And then we have all of the possible ways that you can have n bits, which is what our yeses and noes are. It's all of the possible ways you can have n bits flipped when you have d bits, and in the end, well, basically you've got two exponentials here. You've got an exponential decay because p is less than 1, and then you've got it to the power of n, and n is at least d over 2. So you basically here you've got a decay of p to the d over 2, and here you have an increase because this has factorials in, of course, and if you have d over 2 down here and d over d here, that gives you an exponential increase in the number of possible states there are that could happen. And so you're going to have an exponential increase here and an exponential decrease here, and those two are going to fight against each other. But what you find is that in any case, this exponential is the most powerful, so it really dominates what's going on. So basically what you're going to see is that this is going to be an exponential decrease overall, according to p over 1 minus p to the d over 2. So I should have also said there's 1 minus p to the d here as well. That's getting, and then this can be d over 2, so this whole thing is d over 2. So this is basically what your decay is going to look like. This is the dominant factor in the decay. So this simplification here doesn't explain everything because there are still these entropic factors, but this is basically what you're getting. As you increase the number of repetitions, then the probability that you get more than half affected by noise goes very, very small. And this is what you would expect, really, if you think about it. So if the probability of errors happening is 1 in 10, then what's the probability that more than half get affected? Well, that's quite a lot more than 1 in 10, so it's going to be quite rare. But if you looked at the probability that 1 in 10 get affected, of course that would be relatively high. So in that case the entropic factor would not fight so much against the exponential decay. But because we're requiring this because the level at which errors must occur is that they must occur on at least half of the bits, then for any probability of that happening less than half, then the probability, for any probability of it happening on a single bit of being less than half, then the probability of more than half of the bits getting flipped is very small. It decays exponentially with d. So this is big P, the probability that our message gets misinterpreted, even though we've encoded it in many repetitions. And so we want this to be less than our maximum acceptable error probability, because this is going to be the probability that we get misunderstood. And we can do that for any p less than half by just using enough repetitions. So if we use a certain amount of repetitions and it's still too noisy, then we just throw a few more on, and then each one adds to this exponential decrease, and we will soon get below the limit that we want. So that's for any p less than half. Now if p is more than half, also that's a good way. It's just our encoding needs to be changed, or our decoding at least, because we know that most likely more than half will get flipped in that case. So we have to do a sort of minority voting instead. But p being greater than half is quite a weird scenario, so we don't have to think about that too much. But really, p being equal to half is the only point in which this really doesn't work, because then your p divided by 1 minus p is 1 and you don't get the exponential decay. Okay, so this is a simple example that contains all of the basics of error correction. We have an input, which is some information we want to protect from errors. We have an encoding, which is the way we change the input to make it fault tolerant. In this case, our input is just a bit, either yes or no, and our encoding is to repeat the bit d times. Then we have a transmission step where we are sending it to someone, or even we are just storing it over some time in our hard drive. And at that point, noise is going to affect it and change the encoded message. And then at the end, the receiver will take the message that has been changed by the noise and tries to work out how to undo it. So in this case, you'll get D repetitions where they're not all yes, but a few of them are no, or vice versa. And then you have to work out, okay, well, probably those few ones that are in the minority are the result of noise. So let's flip them back. And then it's the same as being many repetitions of the same thing, and we can deduce what that thing was that was repeated. So so in this case, it's a sending of information. We have some probability little p that things are going to get flipped, and we have some big P sub a that is our maximum acceptable error probability, and we work out how to encode things to get that. If we're storing information, it's slightly different in that the probability that errors will happen, our little p, is going to increase over time. So it will tend to half, which is the bad place, the infinity of probabilities, as it's maximally disordered, as time goes to infinity. So we could just throw on more repetitions the longer we want to store it, just to try and fight against this fact that the probability is increasing. But actually, it's going to get quite close to half quite quickly. And once it's quite close to half, well, it depends on exactly how the probability increases, but if you assume a Markovian noise model, it decays exponentially to half. Well, it's not actually a decay, is it? Because it's increasing. But it tends exponentially to half. So it's sort of, after a few half-lives, you're very close to the probability being half. And at that point, well, your exponential doesn't help you too much because you're exponentially close. P is exponentially close to being half, and so this exponential doesn't help too much. So what you want to do is not just increase the number of repetitions, but do something else. And the way you can do this is just keep decoding and encoding it over time. So you take your input, you encode it, you store it for some time, delta t, which is smaller than the time t that you want to store it for in total, and then after that delta t, some small amount of noise will have happened according to this probability p delta t, and then you decode it, and then you re-encode it, and then you store it again, decode it, re-encode it, and continually around this process. So here I say you decode it and then you re-encode it. So this, here you could imagine, okay, when I get to this stage, I've got lots of yeses and a few nos. So decoding is to say, okay, yeses are in the majority, this was a yes, and then you go to the encoding step and say, okay, now I have to repeat this yes d times, and then so on. But actually we could just do, not just We don't actually have to decode and re-encode fully. We could just try and fix the encoded version. So we could take this yeses with a few no's and say, oh, the no's are in the majority, let's flip those to yeses, and then go around again. And that's more in line with what we're going to do with the quantum case. So we repeat this n times, such that n times delta t is the time that we want to store it for. And then once that's done, we decode and we get our output at the end. And what we find in that case is that the probability that we get the wrong result out after a time t is basically n times the probability that we get the wrong result out after a time delta t. This is actually an upper bound on that. But basically you look at the probability that each round fails and then you just multiply that by n. This gives us a nice expression which we replace n by t over delta t, and then we get our familiar p over 1 minus p to the d over 2 from before. And by rearranging this and substituting in here our maximum acceptable error probability, we can find the maximum time that we can do this for, and we find that it looks like this. So the maximum time, here's some coefficients. So exactly what we choose as our maximum acceptable error probability, or our time interval, determines exactly how long this goes on for. But the main effect is from this exponential. It's 1 minus p over p now, assuming p is less than half, which is what we always do for the repetition code. Then this is greater than 1, and so we have an exponential increase in the maximum lifetime of this memory with the number of repetitions. So this process works great for bits. In 4 bits we take our 0, we repeat it, maybe one of them gets flipped, we identify the one that got flipped, we flip it back, and then so on. Or for 1 we would have the same thing, but it's 1s, and then the last one would get flipped, but this time from 1 to 0, but nevertheless we identify it, and so on. At the very end we get our bit out. But for qubits, this process is not going to be great. So if we just store 0, it'll be fine, and if we just store 1, it'll be fine. But what if we want to store the state plus? So the state plus looks like this. It's the superposition of 0 and 1. So if we put this into the repetition code tells us that every 0 must be replaced by repeating the 0, and every 1 must be replaced by repeating the 1. So yeah, when you have the repetition code in the case of the quantum codes, then you can't just say, let me take this state and repeat it for an arbitrary state, because that would be a violation of the no cloning theorem, which we'll get onto later in the course. So what we have to do is have a basis independent way of doing this, where we say, I'm going to do the repetition code in the 0-1 basis, for example, which means that when I encode a 0, I repeat zeros. When I encode a 1, I repeat 1s. We could instead do a repetition code in the plus-minus basis, which means that we replace plus with a repetition of pluses and minus with a repetition of minuses. But that's not what we're going to do here at this point. So we take the plus state, and then because it's 0 plus 1, and we're doing a repetition code in this example in the 0-1 basis, then we repeat the 0s, repeat the 1s, and this is our encoded repetition code version of the plus state. Now we go through this process. So in this case we'll have a superposition of 0, 0, 0 and 1, 1, 1, and then we get to this point and errors occur, and in this example they're occurring on the last qubit. So then we get a superposition of 0, 0, 1 and 1, 1, 0, and then we go to this point and we measure whether each qubit is 0 or 1, and we collapse down to either the state 0, 0, 1 or 1, 1, 0. We find out the error occurred on the last one because that's in the minority. We can flip that back, and then at this point we'll have 0, 0, 0 or 1, 1, 1, depending on what our measurement outcome was over here, which means that we've detected and we've corrected this bit flip, which is great, but we've also taken our superposition and destroyed it, which is not so great. We want to maintain the entire state, and in order to try and maintain the zeros and the ones, we've destroyed the superposition. So that's not what we want. So inherently we have to extract some information. We have to do a measurement because we need to know, we don't know anything about the errors, and we need to know that, and that is an information extraction if we go from not knowing something to knowing it. And that is a measurement quantum mechanically. So we need to make a measurement, but we have to make sure that that measurement doesn't have effects that we don't want it to have. It doesn't tell us information about things that we don't want to know information about. We need to measure carefully to make sure we only get the information we want to know. So to see how we do this, we can see that even if we just look at bits, we don't actually need the values of these bits to decode. We just need to know domain walls between errors and non-errors. So for example, let's say we start in the all zero state. We've encoded a zero, repeated a zero, and then some errors come along here, 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 and here. And then if we look at the zeros and ones, we can see there are more zeros than ones, and sort of ones are in the minority. But actually, even being completely value agnostic, we can just imagine there's some way of asking a pair of qubits, tell me if you're the same or different. Don't tell me whether you're 0 or 1, just tell me whether you're the same or different. So we ask this pair and they'll say we are different. And we'll ask this pair and they'll say the same, this pair will say the same, this pair will say different, same, 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 different, different, same. And if we had an encoded 1 at the beginning, and errors had occurred in the same places, and we'd ask the same questions, we would get exactly the same answers. Because again, these are different, and these, and everything else is the same. So the information that we're getting in this case of the same and different doesn't tell us anything about whether they're 0 or 1, and so we get the exact same results whether we had an encoded 0 or an encoded 1. All we get is this information which is caused by the errors, these domain walls between errors and non-errors. And this information is sufficient to do decoding, because we know that there are only two possible values, 0 and 1. So we know that if this is a domain and this is another domain, and then this is another domain again, then it has to be the same as that domain. If this domain is different from that one, and this domain is different from that one, then these two domains have to be the same. So then we can separate everything into two domains essentially, and we can see which ones are bigger. We can see that this one, the black one, is the biggest one, and the red one is the smallest one, and we can apply a NOT gate to the minority to correct it, to get rid of the errors. And a NOT gate symmetrically makes 1 zeros and 0s 1s. It's a unitary operation in terms of quantum mechanics, and so it doesn't extract any information, it just does what it needs to do. So just by finding out this same or different information and identifying domains, we can apply a unitary operation which will undo the errors, and through this entire process we didn't find out whether we had encoded a 0 or a 1, and so even if we had a superposition of this and that, we would get the same information out when we asked for same or different, and would be able to correct the errors without disturbing the superposition at all. But the question then is, how do we measure these domain walls? How do we take two qubits and ask them to tell us whether they're the same or different without telling us any additional information? And the way we do that is through the controlled NOT gate. So the controlled NOT gate is a very important unitary, which I haven't talked about yet in the course, but it's not too complex, so it doesn't matter too much. It's a unitary operation that, when applied to the 0, 0 state, will give you the 0, 0 state. When applied to 0, 1, it will give you 0, 1. When applied to 1, 0, however, it will give you 1, 1, and 1, 1 will give you 1, 0. So essentially, it's a quantum version of an XOR gate. So if you know your classical logic gates, then you can understand this in terms of an XOR. It takes these two inputs and it gives you The first input, without being changed, you'll notice 0011 stays as 0011, and the second input is replaced by the XOR of the the second input is replaced by an output, and that is the XOR of the two inputs. So XOR is essentially looking at 2-bit values and seeing if they're the same or different. These are the same, so you get a 0. These are the same, so you get a 0. But these are different, so you get a 1. And these are different, so you get a 1. We can also think of it as looking in some coherent way at whether the first input is in the 0 or the 1 state. If it's 0, then we do nothing to the second qubit, and if it's a 1, then you flip the second qubit. You apply a not to the second qubit, so it goes from 0 to 1 or 1 to 0. So this is a unitary, this is what it does, and hopefully just by that explanation you can see why it's good for the purpose that we have in finding out if 2 bits are the same or different, because inherently it computes an XOR. So well, we don't just use one C0 though, we are going to introduce an additional qubit to act as what we call an ancilla. So here's a case of a repetition code where you have 3 repetitions. So this is an encoded 0, so this is a 0 and a 0 and a 0, although noise has caused this last 0 in this example to be flipped to a 1. So this is an encoded 0, that's why these are all supposed to be 0 at least. If we had an encoded 1, then these would all be 1. But these ancillas always start off in state 0. They don't depend on what we are encoding. They're just sitting there waiting to help. And then what we do is a couple of controlled knots. So this is a depiction of a controlled knot, especially as you find it in the quantum experience. So this end is the one that's looking whether it's a 0 or 1, and this end is the one that's either applying a not or not, depending on the state of this one. And so we when we want to look at whether this one and this one are the same or different, then we do 2 controlled knots, both controlled on one of the ones that we want to know about, and both targeted. So the end that gets the knot, depending on what the other end is doing, is called the target, and the one that decides whether the knot gets applied or not is called a control. So these are both controlled on the code qubits and targeted on the ancilla. And so in a case like this where they're both the same, well, here they're both 0. So this one's 0, so no knot happens here. This 0 passes through and stays a 0. This one's also 0, so no knot happens here. So this 0 passes through and remains a 0. So then when we measure it, so this is a measurement gate, then we will get the output 0. Similarly, if they had both been 1, then this one would see a 1 here and then do a knot, so this 0 would become a 1, and then this would see a 1 and do a knot, so this 1 would be flipped back to 0 and we'd still get 0. So whether these are both 0 or whether they are both 1, we get the output 0 here. So yeah, in both cases where these 2 bit values are the same, we get the output 0. However, if they are different, then, well, in this case we've got a 0, so nothing happens here. This 0 remains 0. But here we have a 1, so there's a knot being performed here. So I've made this orange just to show that a knot is happening. There's no actual physical difference in the C knot. So this 0 gets turned into a 1, and so because it's been on the receiving end of only one knot, then it remains a 1 at the end. We measure it, we find a 1. And then by looking at these values, we can see, okay, we measured, so this is telling us whether the first 2 are the same or different, and it tells us with a 0 that they are the same. This one tells us whether the second 2 are the same or different, and it tells us with a 1 that they are different. So we can infer, okay, well these 2 are the same, but this one is different from those 2, so this one is in the minority, this one is the error, and it needs to get flipped. So we're taking this information, processing it, and working out that this guy needs to be flipped, and then that gives us back our original 000 state. So we started off with an encoded 000, some errors happened to cause us a 1, to cause it to become a 1. We did these C0s, we did these measurements. From that result, we inferred that we had to flip this bit. And this whole process would have been the same whether we repeated a 0 or repeated a 1, or had a superposition of a repeated 0 and a repeated 1, and therefore would be completely blind to what we encoded. It wouldn't tell us about what we encoded, and it would preserve superpositions. Now, it won't be too relevant for the rest of this lecture, but it's good to keep in mind that this corresponds to measuring an observable, which is ZZ. So this process of taking an additional qubit and doing some C0s, we can also think of more simply in quantum mechanical language as just being the measurement of a certain observable, and this is the observable that we're doing. So, yeah, fundamentally we can think of it in terms of measuring this observable, but in terms of actual implementation, we do it in terms of using this process using an ancilla and 2 C0s. Okay. So, what we can then do is repeat this process to protect our state from arbitrary bit flip noise for as long as we want. So bit flip noise means, well, sigma x is a unitary that can be applied to the system. So we can think of a little gremlin sitting next to each qubit and deciding randomly with probability p whether or not it's going to apply this sigma x, which is our bit flip. We can protect against the effects of these gremlins by taking our arbitrary state that we want to store, turning it into this entangled state. Now we repeat d times, and this is d equals 3, each of these bits, and then we do this process many times where we prepare ancillas that sit between pairs of the code qubits. We do these controlled knots to find out whether the code qubits are the same or different. We measure, and then we use that information to, well, we could, as I said in the last slide, use that information to actually physically perform knots, which are X gates, on our qubits to undo the effect of noise. Or we could just keep track of all of this information, which is the easiest thing to do, because we don't have to go in there and actually poke around with the state. But also, it's any quantum operations also come with some noise. So by just keeping track of the information and not doing anything physically, we can also reduce the amount of noise we put in the system. So we just repeatedly look at this information, and then at the end we read out these 3 things, and rather than just doing a majority voting of these 3 results, we take the information of these 3 results. We take also all of the information that we had extracted over time, and then we look at how the domain rules move around and shift, and majorities and minorities and whatnot, and in the end we deduce where the errors were and where is good, and then we, depending on that, we can either say the result that we got from here was correct, or we can deduce from all of the information we got that between here and here this qubit suffered an error, and in this case we correct it. So basically, in this example, we're taking this to be our output up to some correction, which depends on all of the information we got. If we didn't have this bit in the middle, and we only, oh sorry, I should also say that we've got the encoding step going on here. So we've got these initial zeros. So usually our quantum computer is always initialized in the state where everything's 0. And if we want to encode the state 1, then we perform an X here, here, and here, so that we get a 1, 1, 1. And if we want to encode 0, then we don't do an X here and here. So this X to the B is either, it depends on the bit value that we want to store. So it's B. If B equals 0, then this is just the identity, and if B equals 1, then it's an actual X. So this is our encoding. We take our initial zeros and either flip them or not, depending on whether we want to store a 0 or a 1. And then at the end we measure. Let's forget about this bit in the middle for now, if we didn't have this bit in the middle, at the end here we'd just be doing majority voting. So we could just, so then the effect of this is just to see, is this in the majority or the minority? And if it's in the majority, then we do nothing here, and we just accept whatever it told us as the output. But if we find by looking at the results that it's in the minority, then we flip it. So we come up with this correction operation which will flip it, and then we take it as the output. So this is just saying, instead of reading out the information from the majority in all cases, which is what we want to do in general, it's just simpler in terms of writing a gate to set, or writing a circuit, or creating a process to say that we are going to read out the information always from the same qubit, but we're going to correct it or not, depending on whether it's in the minority or not. And then if we introduce all of this stuff in the middle, we've just got a lot more information to introduce, to also incorporate into this decision as to whether we have to correct this output or not. Okay, so by repeating this process, yeah, we can store, we can protect information against bit flip noise. And just as we were talking about with the repetition code earlier, then this will be exponentially suppressed. Noise will be exponentially suppressed as we increase the number of repetitions, and we can increase the lifetime against which we protect against bit flip noise exponentially with the number of repetitions. However, we do nothing about dephasing. So for example, imagine our little gremlin might also do a sigma z, might also choose to apply a sigma z to our state, which would take our encoded state A000 plus B111 and give us A000 minus B111. This is a different superposition state. This is an error. It's bad. So do we detect and correct this? No. Our process is completely insensitive to the nature of the superposition. So if the nature of the superposition changes, we don't see it. If it doesn't flip any bits, we don't see it. And if we don't see it, we can't correct it. And also, the same effect would be had whether you did the sigma z on the first qubit, the second qubit, or the third qubit, because of this symmetry. The sigma z introduces a phase difference between 0 and 1, and because we've repeated the zeros and the ones across the entire range of repetitions, then we can do that sigma z anywhere and it'll have the same effect. So the probability of a sigma z happening is increased with the number of repetitions, because we give more opportunities for this noise to occur. So even though our sigma x's are decreasing exponentially, our sigma z's are increasing. Not exponentially, but still they're increasing. So that is bad, and we have to try and work out ways to fix it. So we can think then about what is wrong with the repetition code in order to try and work out how to fix it. And what is right with it, of course, which we want to preserve. So when coming up with a new code, we want a new code which does all of the things that the repetition code does correctly with regard to bit flip noise, but avoids everything that it does badly with regard to phase flip noise. So what is good about it with regard to bit flip noise? Well, the way I'm going to look at it now is in quite an abstract way, and it's going to lead us towards the sort of philosophy of what we call topological quantum codes, topological quantum error correction. So it will sound a bit abstract and weird, but that's just because we're going in this abstract and weird direction of topology. There's a less abstract and weird way you could do it, and you could just say, like, well, let's just take a free repetition code and get a little bit of suppression. We'll get a fair amount of suppression here and a little bit of increase, and let's use those free repetition codes as the free inputs to another free repetition code, which actually in this case would then have 9 qubits. But the second one will be repeating the pluses and the minuses instead of the zeros and the ones. So that will get a suppression of exponential suppression of the phase flip noise and a little bit of increase in the bit flip noise. But because so the exponential suppression of the phase flip noise will account for the fact that it increased before, and the increase in the bit flip noise will not be so bad because it got exponentially suppressed before. And then we can just keep doing this where we swap between these two types of repetition code in order to be a little bit more symmetric between the bit flip noise and the phase flip noise. And if we do that, it's called the Shor code. But we're not aiming towards the Shor code. Later in the course we'll be looking at the surface code, so we're analyzing this in a way that's more compatible for that. So we can think of an isolated bit flip as creating basically a pair of domain walls, and we're going to call these defects. What happens if we have more sigma x's? Well, if another big bit flip happens right next to the one before, it basically grows this domain, so it moves a domain wall. It moves one of these defects. If we have a bit flip occur somewhere else, it will create a new pair of defects. If we have, because it will create a new domain. If we have a bit flip between these two domains, it will merge the two domains, and so it effectively annihilates a pair of domain walls. It annihilates a pair of defects. And if we want a logical error, it means we need to create a pair of defects which have a distance of d over 2, more than d over 2 between them, because in this case we would misinterpret the domains, and we would actually grow this domain. We would see that there are more bits in this domain than the other one. We would misinterpret the grey one, the 0 one, as being the one that was the result of errors. So we would end up growing this domain so that it covers the entire thing and therefore has no domain walls. So we need if we had a distance d over 2 between two defects, then that would cause a logical error. Or if we had many defects which were a similarly large scale effect, then we could also cause a logical error. So basically we can think of the repetition code as a little one-dimensional universe in which these defects are its particles. They are created by bit flip noise, created as pairs out of the vacuum, and then they can be moved around by more bit flips, and they can be annihilated by more bit flips. And we need large scale effects with these particles in order to cause a logical error. So there's our abstract interpretation of what the repetition code is that we are going to try and preserve when we generalize to something that is more quantumly useful. So why doesn't it protect against phase flip noise? And the reason for this is that measurement is too easy. Even when you've encoded information, it is very easy to read out that information. So you just look at any bit and it will tell you what you encoded, because the information is repeated across everything. So as long as you don't have errors, just taking a little measurement of any qubit tells you what you've got. And the whole point of dephasing is that it distinguishes between the 0 and the 1 state. So effectively, dephasing is the environment having a quick peek at our information. So if it's easy for us to do, it's easy for the environment to do. So that is why it's bad. Now consider instead not measuring in the 0-1 basis, which is us trying to work out whether 0 or 1, measure 0 or 1 in the encoded information. Let's consider us measuring in the x basis instead. So for example, we have the plus state, which is 0 plus 1, the minus state, which is 0 minus 1. We encode those and they become 0, 0, 0, or however many repetitions, plus 1, 1, 1, or 0, 0, 0, minus 1, 1, 1. So how do we do a measurement which can distinguish between these two encoded states? If they're on a single qubit, we just measure in the 0, 1, in the plus minus basis. But spread over d qubits, we can't just measure a single qubit and it will tell us whether we've encoded plus or minus. We have to do a measurement that involves all of the qubits. So it's very easy to measure in the 0-1 basis, but it's very hard to measure in the plus minus basis. So this is the x basis. It's the eigenstates of the sigma x operation that is hard. and this is the eigenstates of sigma z that is easy. So this is, again, things that are associated with sigma z are hard to do. Bad things associated with sigma z are hard to do. For the environment to do bit flips, which are sigma x's, and flip our stored information from 0 to 1, that is difficult because of our repetitions. Also, if the environment wants to take a little peek at the x basis states distinguished between plus and minus, that is also hard. Whereas for sigma z's to occur, that's very easy, and for sigma z's to get measured, that's very easy. So this is the same problem as before, that it is easy for sigma z's to be applied as unitaries, but it's also easy for them to be measured. It's easy for, hard for sigma x's to have a big effect as unitaries, because we can just identify the minorities on which they have occurred and get rid of them. It's also very hard for the environment to measure in the sigma x basis. So when we come up with something better which protects us against phase flip noise, it also means that it must be difficult for us to measure in the 0-1 basis. So not too difficult, not so difficult we can't do it, but it must be fairly straightforward when us, who know how we've encoded it, want to do it. But for noise that doesn't know how we encoded it, it would have to go for a random and therefore quite unlikely process in order to measure it successfully. So yeah, these are the reasons why the repetition code is not so great. And when we look at the surface code, we'll look at how we overcome these. I should also talk about imperfect measurements. I've assumed throughout that when you measure the ancillas, then it will tell you what 0 will tell you if the two bits were the same, and 1 will tell you if they're different. So where did that happen? So here some noise happened which flipped this bit, and then in the rest of this process no noise happens. We do some controlled knots, they're perfect. More controlled knots, also perfect. The qubit idles during this process, nothing's going to happen there either. We measure, it tells us exactly what the right answer is, completely perfect. All of these assumptions are completely unrealistic. None of them are perfect. This whole process will also be noisy, meaning that this measurement result can give us spurious information. So how do we account for that? Well, let's consider just having a single qubit, and we have a probability when we measure it that the measurement is going to lie with some probability p. So this should really be a small p. But we're still going to have the quite unrealistic assumption that the measurement does not disturb the qubit at all beyond being projective, of course. And how do we, so in this case, how do we extract information correctly? Again, it's repetition, we just keep repeating. But now it's kind of repetition not across many qubits, so a space-like repetition. It's repetition over many measurements, one after the other, so it's a time-like repetition. We measure and it tells us 0, we measure again, it tells us 0, we measure again, it tells us 0, we measure again. Oh, here's an example of a lie. It tells us 1, we measure again, it tells us 0, we measure again, it tells us 0. And by looking at that, okay, mostly it's telling us 0. This one time it said 1. That was a lie. And we can use the same decoding where we just we find domain walls, we identify the minority, and we flip it. So lies create pairs of defects in the time direction, effectively, and sigma x's bit flips create defects in the space direction. So if we combine the repetition code with repeated measurements, then what we get is effectively our defects living on a two-dimensional grid. This is from a great paper on the surface code, which is worth checking out. So if you have the repetition code, so this is an example of a repetition code here, you can imagine the code qubits living on the edges and the ancilla qubits living on the vertices. Then this is a repetition across many qubits, and this is repeated measurement over time, then what this is showing us is, well, suppose a bit flip happened here, then the ancillas either side will be saying, okay, this qubit and this qubit are no longer equal, and this qubit and this qubit are no longer equal. So these ancillas are giving us these two defects that are now separated in space, and they will also keep on appearing. If we don't step in and correct them, they'll keep on appearing for the rest of time. But let's just say we only record these with a little dot when we see something we didn't expect. So we started off, everything was perfect, we didn't see any defects, then this error happened, we saw two defects, so we record them with dots, and then we go on. We measure again, we still see these two defects, but we expected them this time, because they were there before, we didn't do anything about them, they're expected, and so we don't record them. No other errors happen. Then we come along here, and we find this ancilla tells us that something's wrong, but this one doesn't. So here we record a defect, because we expected there to be nothing and there was something, and also here we're recording a defect. So what's going on here? It could have been that there were two bit flips on this qubit and this qubit, creating a domain with these two domain walls, but we don't know yet, because measurements can sometimes lie, and therefore it could be that that assumption is not true. And we measure again, and this ancilla now tells us that there's a defect. It didn't tell us that before, so it's unexpected, we record that. This one still tells us that something's going wrong, but it did so before, so we expect it. This one tells us the opposite than it told us before. So maybe here it said something's wrong, and then here it said, oh, no it isn't. So here it was unexpected for it to tell us that something was wrong, so we put the dot. Here we expected it to keep on telling us that something was wrong, but it didn't. It told us everything was okay, so we put a dot. So we're putting a dot every time that the ancilla tells us something we don't expect. So the ancilla tells us either, oh, my two neighbours are the same, which is good, or it tells us my two neighbours are different. And whenever it changes its tune, whenever it tells us something that it didn't tell us before, we put a dot. So then here we can see that there's some results of measurement errors. So maybe here it's saying they're the same, my two neighbours are the same, my two neighbours are the same, my two neighbours are the same, oh, my two neighbours are different, oh, my two neighbours are the same actually, and the same and the same and so on. Then what we see here is that actually when we measured that they were different, that was measurement noise. That was the measurement telling a lie, and so we have these two time-like separated defects. And here we have an example that maybe here there was a bit flip, and here it didn't get seen because the measurement lied to us, but next time it stops lying, and so we have a pair of defects separated in space and time due to that measurement noise. And here we've got another pair that are separated in space, and here we've got another space-time separated pair. So what we're saying is that when we have measurement noise, we have to keep on repeatedly measuring, which actually we're doing anyway. But before we assumed that each time we repeatedly measured, it was a completely independent thing that we could look at majorities and minorities. But now we see that when we repeatedly measure, actually we're going to have to look at what we call syndrome changes. So this information we get from the ancilla we call a syndrome. We look for syndrome changes, and it's the syndrome changes that are now going to be our defect. When it tells us that everything is bad, when it just told us everything was okay, that's a syndrome change. That's a defect. If it tells us everything's bad when it just told us before that everything's bad, that's not a syndrome change, so it's not a defect. When it tells us everything's good when it previously told us everything was bad, that is a syndrome change, so it is a defect. And if we look at the pattern of defects we get, they basically live now on a two-dimensional grid. And I'm calling it space-like and time-like, so practically the information that is generated that causes this pattern of defects is due to repetitions of the measurement which occur ordered in time, and these come from repetitions over many qubits, which is space-like. But in terms of the defects themselves, they're basically living on a grid of two spatial dimensions, and this is not a world line in space and time of a defect. That's just, these space-like and time-like are just for us to remember where the data came from. Once we are looking at these and how they move around in this two-dimensional universe, it's effectively a universe of two spatial dimensions. But if that didn't make much sense, then hopefully it'll make more sense when we look more at the surface code later, in which we will revisit many of these concepts. Also, check out this paper, which, as I said before, is great. So basically, noisy measurements increase the space of our universe by one dimension. If we have a repetition code where defects used to live on a 1D universe when measurements were perfect, now they live in a 2D universe. And when we look at the surface code in which the defects with perfect measurements would live in a 2D universe, noisy measurements make them live in a 3D universe effectively. Okay, so now we can go to actual experiments. We can run repetition codes with current devices. Current devices have many qubits. With many qubits we can repeat bit values across those many qubits. We can take a line of qubits and use them alternately as code qubits, where we're going to put our repeated zeros or repeated ones, and the ones between them we use as ancillas. Then we implement the controlled knots, we extract information, and all is well. Now, with a limited size version of this, an experiment has been done which has repeatedly done many rounds, just as we have here, and that was a paper by Google back in 2015. But often it's quite hard to do measurements and then do other stuff after the measurement. So in that case, they initialized the ancilla, did the controlled knots, did a measurement, used that, then reinitialized the ancilla after the measurement, and continued. But often in solid state systems like superconducting qubits, which we have on the cloud at the moment, measurement takes a long time, and so really we would want to just measure and then give up. Also, measuring selectively some parts of some qubits on a device and not others is quite difficult, because there will be crosstalk between the qubits. So with current implementations of devices on the cloud, you can only ever measure and then you're done. So you can't do many repetitions of this, but you can do one. So we take our initial zero state for the code qubits. We either keep them as they are if we want to prepare a bit state 0. We flip them if we want to prepare a 1. We do our controlled knots to tell the ancillas whether they're the same or different. This will tell us about any noise that has occurred in the preparation, in the flipping, or just in this amount of time. Then finally we measure everything. We measure the 3 code qubits, and we measure the 2 ancilla qubits. Or, well, this is if we have a D equals 3 code. Of course, we'll have D code qubits and D minus 1 ancilla qubits in general. Then we take our output and we try and work out, by processing this information, we try and work out what it was that we encoded just from this output. Of course we know what we encoded, but we have to pretend we forgot. From this we can calculate the probability that the bit value we decode is different from the bit value that was encoded. And we can compare that with storing the information over the same time, just on a single qubit. So if you go to github.com/digadoku/repetition_code, you will see an implementation of this on IBM's 16-qubit processor, and you can run it yourself, and you can try different variations. So for example, with 3 code qubits, this is a graph of qubit against probability of getting the output 1 at the end. And so here I've encoded a 1. So this is a code qubit I prepared in state 1. This is an ancilla in state 0, code qubit in state 1, ancilla in state 0, code qubit in state 1, and here next to the code is just a single qubit which is also encoding the state 1, and then the rest is not being used, so it's still in the 0 state. You see, because of noise, the probability of 1 should be 1, because this is a 1, but it's less than 1 because of noise. This should be, probability of 1 should be 0, because this is a 0, but it's more than that, again because of noise. So that's the yellow where we're encoding a 1, and then the blue we're encoding a 0, so everything's 0, both code and ancilla. And this is the same for 8 qubits, so 1, 0, 1, 0, 1, 0, 1, 0. Well, you know what a zigzag is. So that gives you a bit of an idea. I think did I go the wrong way there? Sorry about this. Okay, full versus partial decoding actually. One test that we can do when we get this data is we can note that actually we can just ignore the ancillas. We could just do majority voting on the free code qubits. This whole ancilla thing is supposed to improve things. It's supposed to extend the amount of time that we can store it for, at least a little bit for this one round. But it involves doing C-naughts. And so does it actually improve things? Are C-naughts just a source of noise? Do the C-naughts even work? Do we get any useful information on these ancillas? We can test that by looking at the decoding when we only use the code qubits and looking at the decoding for the entire thing. So I'm calling these full decoding when we use the ancillary information as well, and partial decoding when we don't. And we find that if we look at the error probability as it changes over code distance, then typically full decoding has a smaller, significantly smaller error probability than partial decoding. And so indeed the ancillars are telling us useful information. And here the green line is a comparison against the single qubit memory, which I've just taken the best single qubit memory over all of the instances to compare against. And we also find that, at least for large code distances, both full and partial decoding typically beat it. So using an error correcting code to store a bit is better than using a single qubit to store a bit, which is precisely what we want. We want our repeating to convey information more accurately than just not repeating at all. And we find that. So we're finding good stuff. This is a logarithmic plot, so we're seeing sort of exponential decay, which we want with the code distance. We're seeing that actually using the ancillas is good, which is also good. We're seeing that our code is better than a single qubit, so everything is awesome. And also we can use this information to see that we can actually do better than just majority voting. You can use experimental data to determine the most likely encoded bit. So for example, if we look at the probability that the probability that we'll get a certain number of ones in the code qubit result. So if we encode a 0, well basically we start off with a load of zeros, we do some C-naughts which shouldn't change them from being zeros, and then we measure them. So ideally they should all come out 0. So what is so if we look at the number of ones, I think I said the number of zeros before, there should be no ones in that result. Any ones means that errors have happened. So the probability of there being no ones should be pretty high. The probability of there being one should be, well, also quite high, but it should be lower because it's evidence that some noise has occurred. And then progressively, as we get more ones, then the probability should go down because it means we're getting more and more noise. On the other hand, if we're encoding a 1, we should get d1s at the end. So this is a d equals 8 example. And the probability of getting very few ones should be very low, which is why we see it go down in the other way. And there'll be a crossover point between the two. And so in the end, if we get, so this is for just a partial decoding as a simple example. So if we look at only the code qubits, and we can then look at the number of ones and compare them to this graph. If it's less than the crossover point, we know that it's more likely that it's an encoded 0. If it's more than the crossover point, we know that it's more likely that it's an encoded 1. And that crossover point is not necessarily going to occur at half. This is d equals 8, so we expect it to occur at 4. It doesn't. It occurs between 3 and 4, and in fact nearer to 3. So it's accounting for the fact that it's accounting for the actual realistic nature of noise in the device, which isn't symmetric, that 0 becomes 1 with the same probability that 1 becomes 0, but actually there is an asymmetry, that it's more likely to have these transitions where 1 becomes 0 than vice versa. And so doing this we can explain counterintuitive finite size effects. So a fun thing about this is to find the weird little effects and try and explain them, because that gives us a bit more information, a bit more of an insight into the device. And here if we look at the low code distance, full decoding gets a higher error probability than partial decoding. So why is that? How can that be? Well, it's partly due to the way we define these probabilities, and it's also due to the fact that larger codes are more able to account for the fact that we get shifts in this graph. So for here, if we look at 3 repetitions, we have a shift in this crossover point, quite a significant distance, but it's still between 1 and 2, so we'd still do majority voting. Whereas we've got pretty much the same shift here with 7 repetitions, but just because we have more stuff going on, more markers down on this bottom, then it's no longer between 3 and 4, but it's shifted beyond into between 2 and 3. So when we have more repetitions, we can actually better account for the fact that we've got shifts going on due to the realistic nature of noise. But that does not occur, or at least doesn't occur with an even more drastic amount of noise for smaller codes. So smaller codes are less able to account for this, and that's why we'll get weird effects. But I'll leave you to ruminate over where that weird effect comes from, or look at the paper that's referenced in the GitHub that I've written on this. Okay, so that's all I want to tell you about the repetition code. If there's any questions, we can address them next week, or also we'll go over many of these things, especially the more abstract things, when we look at the surface code later on in the course. But I would encourage you to have a go at actually implementing repetition codes using the quantum experience, either using the GUI as you've used before for the exercises, just dragging and dropping and looking at CSV files, or by going to the GitHub and cloning my project and running it yourself and working out different variations on it, because this is the kind of useful thing that we can do in the field at the moment, and it's really at the cutting edge, but it's still something that you can get involved in. So if that's something you're interested in, give it a go. Okay, so thank you for listening, and I will be back in Basel next week after I finish giving a talk in Dresden on, guess what? The repetition code. That shows you how cutting edge it is. I'm away because I'm talking about the repetition code at a conference. Okay, great. Thanks. Bye.